Next numerical. The network shown in the figure has acquired steady state for switch closed at t less than 0. At t is equal to 0, the switch is open. Obtain I of t for t greater than 0. So the switch was closed at t is less than 0. It has already attained the steady state condition. This they have mentioned in the question. So at t is equal to 0 minus the switch is closed and the network has acquired the steady state. Hence, the inductor is now acting as a short circuit because the current is already flowing into it and it has attained the steady state. Hence, it is replaced by the short circuit. So, the current through the inductor, the current through the inductor is I of 0 minus. And this is a total current IT of 0 minus. So IT of 0 minus is how to calculate IT of 0 minus. This is two resistances in parallel, 4 into 4 divided by 4 plus 4 plus 10 ohms. So that will give us total 12 ohms resistance. So voltage divided by 12 ohms resistance will give me a 3 amps as the total current of the circuit, which is IT of 0 minus. So once I get IT of 0 minus, I can able to calculate the current flowing through the inductor, that is I of 0 minus, which is equal to the branch current. If I want the inductor current which is flowing in this, so this is equal to the total current, which is 3 into the resistance of the other branch, that is 4, divided by the 4 total resistance, which is 4 plus 4. So this is written here. So simplifying this, I get the inductor current to be 1.5 amps. Since the current to the inductor cannot change instantaneously, at I of 0 plus also the current will remain same as 1.5 amps. When the switch is closed, it is t is equal to 0 plus, the inductor current will not change instantaneously. Okay, so what was the previous current? The same current will be at I of 0 plus, which is equal to 1.5 amps. And at t is equal and t greater than 0, at t greater than 0, the switch is now open. So the circuit which we have will be only this much we need to consider. Okay, so 2 4 ohm resistor and 2 Henry inductor along with the current source, which is 1.5 amps. So this 1.5 amps can be replaced by this is replaced by the voltage source. So we had so like this was the circuit. There was a 4 ohms. So there is an inductor and there was a current source of 1.5. So this was 2, correct? So this was 2 Henry and this was around 1.5. So this is the inductor value and this is the value of the current. So we have converted into, so by using source transformation, we have converted into voltage source along with the series resistance. What we have converted? Current source along with the parallel resistance. So this current source along with the parallel resistance can be replaced by the voltage source in the series resistance. How? V is equal to I into R. So V is what? V is equal to I into R. V is equal to 1.5 into, here the inductor value we need to write, which is equal to, so here the value of current voltage will be equal to 3 volt, which is written here. Okay, and since the direction of the current is in the downward direction, so current will flow in this direction, right? So this is minus and this is plus. Battery terminals we need to indicate, and this value of inductor is written here in series with the voltage. So this is called as source transformation method. Okay, and now we will apply what? We will apply the KVL in order to calculate the current I of S. Okay, for that we will convert the circuit from the time domain into the frequency domain. As I told you, time domain, the value of L will change in the frequency domain to LS. Okay, so this is time domain and this is frequency domain. We convert in order to be easier. Okay, in time domain it will be slightly difficult. in frequency domain, the calculation seems to be much easier. So we will convert this from time domain to frequency domain as Ls. That is why we have written here 2s. Okay, and this current I of t will become equal to I of s. Applying the KVL, here it is from the direction of the current, so it is plus and minus entering terminal. Okay, plus and minus entering terminal, plus and minus entering terminal of the current. So it is minus 4 into I of s. Okay, minus 4 into I of s again for this, and minus s 2s I of s for the inductor, plus the 3-volt battery, okay, which is equal to 0. So from this I of s is the only variable. From this I get the value of I of s as 3 divided by 2s plus 8. Okay, so here if I take 2 common, okay, 2 common, so it will be 3 by 2, which is 1.4, and remaining is s plus 4, okay, which I have written it here. And taking the inverse Laplace transform, okay, I of s will become I of t, and this 1.5 I am writing here same as it is, and 1 divided by s plus 4. Laplace transform of 1 divided by s, inverse Laplace transform of 1 divided by s plus 4 is given as e raised to minus 4t. Okay, so which I have written here. So at t is greater than 0. So this completes the numerical. Next, we will move on to the next numerical. In the network shown, the switch is closed for a long time at t is equal to 0. The switch was closed before and the switch is opened at t is equal to 0. Okay. Find the current through the capacitor. So this is the circuit. So it is open at t is equal to 0. That means this was closed before. The switch was closed at t is equal to 0 minus. Okay, so this is a circuit. So I1 of t is mentioned here and I2 of t is mentioned here, V of t is mentioned. So at t is equal to 0 minus, the switch is closed and the steady state condition is reached. Okay, steady state condition has been reached. Okay, so this, when the switch is closed, so this is going to be a short circuit. Okay, this is going to be a short circuit. So there will not be, okay, the current which will not flow here. Okay. So the voltage across the capacitor is going to be 0. Okay, so this is a short circuit. So voltage across the short circuit is equal to 0. So t is 0 plus. Okay, instantaneously as soon as you close this, open this switch, the voltage across the capacitor does not change. Okay, so it will remain same as the previous value. So which is at t is equal to 0 plus, Vc of 0 plus is equal to 0. So this will remain same. So after some time, it is t is greater than 0. What will happen? So there is a switch which is open now. Okay, the circuit will be this now. Okay, the switch is open. So only this part of the circuit we will consider. Only this part of the circuit we need to consider at t greater than 0. So this I am rewriting. Okay, now the switch is open. So this will not exist. This branch will not exist. There will be a 2 amp current source along with this part of the circuit. So this I will rewrite here. So I'm rewriting it here. Okay, so I'm rewriting at t is greater than 0. The switch is open, which was here. So this will be open circuit. So this I'm not writing here. So our circuit will be as shown here. Again, I am converting the time domain circuit to frequency domain. Okay, so the current source of 2 amps is converted to 2 divided by S. Okay, step current, and the capacitor is half, given as 0.5 farad. So it will be 2 by S when I convert it into frequency domain, and the resistance value will remain same. So applying KVL to this loop, okay, applying KVL to this loop which I have mentioned here. So I get 2 by S, I of S, okay. Then there is a I1 of S, 2 divided by S, I1 of S. Why I am writing? See, my direction I have taken in the clockwise, but this current I1 of S is coming in the opposite direction. That is why here I have taken plus, okay. So I1 of S and 2 by S, I1 of S we get, which is equal to I2 of S into 1 ohms. Okay, so call this as equation number 1. Then KCL at node for t greater than 0. So incoming at this node, we are applying KCL. Incoming current is 2 by S, and this one I1 of S is outgoing, I2 of S is outgoing. So incoming current is equal to outgoing current. So now put the value of equation 2 in equation 1. Okay, so value of I2 that is I2 of S, I2 of S value I will substitute from the equation number 2 in the equation number 1. So this is the value of I2 of S I have taken from equation number 2. 2 divided by S minus 1 I1 of S. So from this equation only I1 of S is a variable. So I get I1 of S to be as 1 divided by S plus 1. So taking inverse Laplace transform of this, we get 1 divided by S plus 1 inverse Laplace transform is e raised to minus. Okay, so this completes the